Is the world we see nothing but an illusion? Physicists have proven that the universe does not exist, and it's really true. What we think is real doesn't actually exist from a scientific point of view. Everything is a perfect illusion, as if created for us. We live within this illusion and explore it now. We are on the verge of a breakthrough to uncover the biggest lie of all time. Is matter really real? It seems so when you put your plate on the table. It stops, and you can take the food into your body. You will notice that this act has an effect. You hear your digestion and gain strength through the food. There is no question that the world of matter exists. Somehow we can kill ourselves with weapons, or rather destroy our bodies in the material world, but recent studies show that the world of matter is nothing more than a hollow projection created for us to experience as protagonists in this world. We may be far more than we appear to be. We may, in fact, be something quite different from mortal bodies with a brain and a heart. So far, scientists say that when the body is destroyed, the human being dies, and quite a few scientists claim that this must definitely be the end of life and existence, but there is evidence that our bodies are just condensations within three-dimensional space, possibly controlled by what religious people might call a soul. Similarly to Avatar, we could simultaneously exist in another world, sleep there, and dream our lives as avatars on Earth. Then this world here would be nothing more than a puppet show. In a way, we ourselves are players and protagonists, but most of us are not aware of this. The theory of relativity is not the measure of all things. Was Einstein wrong when he proposed the theory of relativity? Some modern theories, such as quantum gravity and string theory, call his assumptions into question. The theory of relativity does not work on a microscopic scale. Quantum physics and relativity often contradict each other. There must be one or more levels that unite the two. There is no other way, because quantum theory is the theory of the world of the smallest particles, the quant of light, and these are the building blocks of all large phenomena. Einstein's theory of relativity refers to the universe as space to street stars, planets, and the effects in the world of visible objects, but these objects are all made up of light, quant, and they do not behave as if matter is real. Einstein's theories remain fundamental, but science is evolving at the moment. We are at a point where this type of physics is no longer getting anywhere. The latest discoveries of the James Webb Space Telescope can no longer be described with the old physical theories. Einstein's concept of space and time must have been incomplete. Quantum mechanics reveals phenomena that his theory does not explain. Black holes and singularities contradict the general theory of relativity in some important points. The existence of dark matter and dark energy remains a mystery. Space and time might not be fundamental quantities, but much more flexible than previously assumed. The connection between gravity and quantum mechanics is also still unclear. The latest findings show that gravity may not actually be a force, but rather a curvature of spacetime caused by masses and energy. Some scientists suspect that space and time themselves could consist of tiny quantum-like structures. These structures could behave in ways that we do not yet fully understand. They may possess some kind of intelligence or represent some form of force or life that we could not yet imagine. There is evidence that the physical forces in the universe have changed over time, which would suggest that the universe is undergoing some kind of evolution that resembles life. Einstein's work is a milestone, but the search for a unified theory continues. However, if it turns out that the universe is just as changeable a hollow projection as we are, we have a poor chance of approaching the truth with the old methods of physics. Then we will need superperception or completely new branches of science to unravel the mystery of the cosmos. How does hollow projection work, and who creates it? So if everything is just a hollow projection, where does it come from, and how is it structured? The idea is essentially based on the concept that all the information that creates our three-dimensional universe could be stored on a two-dimensional surface. This theory has its origins in quantum mechanics and the general theory of relativity. Quantum mechanics discovered that quanta are nothing more than information carriers that are incredibly changeable. They can become a table, and thus convert the information of a table to planet Earth, or they can become any other matter, but even if they form themselves, they have the fascinating property of immediately dissolving their form again if they are not measured or observed. In quantum physics terms, this means that your table disappears when you or nobody else is looking. Hollow projection theory assumes that our three-dimensional universe is just a fairly loose projection of information stored on a two-dimensional surface. The idea originates from physicists such as Gerard T. Hoof and Leonard Susskind, and was first introduced in the late 1970s. The decisive factor was the observations made in the vicinity of a black hole, which showed that the amount of information contained in a certain volume of space is limited by the surface of this volume, and not by its volume itself. This contradicts the classical understanding of information in space, and could mean that the spatial dimensions themselves could be wandering phenomena controlled by deeper physical levels. In practical terms, this would mean for our known universe that every piece of information required to construct and maintain this projection is theoretically stored on a two-dimensional surface at the edge of the universe. This information is then projected in such a way that a three-dimensional space with material objects and physical phenomena appears optically a universe of pure consciousness. Our brain plays another key role in this scenario. We can only perceive the world and the universe through our brain and our senses. We basically do not see what is really out there. We only see what the brain lets us see in the holographic universe. Gravity is a result of the projection of information from the two-dimensional surface. This means that gravity is not really a force in the traditional sense, but a dynamic property of the holographic projection. In a holographic universe, we play an essential role as conscious observers. We could be experiencers and creators in equal measure. Now, it has not been scientifically proven that a table really disappears when nobody is looking, nor can we monitor this in an experiment, because the camera with which we observe would be equivalent to a measurement that maintains the shape of the table. Another exciting idea in this context could be the role of consciousness. Scientists don't really know what consciousness is yet, but it's certainly instrumental in shaping quant from the wave to the particle state. Now, it could be that the whole universe is infused with a kind of consciousness that shapes and sustains it. Our consciousness is only a part of the greater whole of consciousness, and we are co-creators, but we don't have to worry about the table remaining a table. For example, is the speed of light the problem? Do you remember from your school lessons that the speed of light is the measure of all things in space? Einstein spent his life researching the forces and phenomena in the universe and came to the conclusion that all phenomena and forces are dependent or relative to each other. Time is dependent on the location of the observer. Acceleration influences time, and the speed of light supposedly sets absolute limits, but this could be a mistake in our physics if the nature of light is possibly completely different from what we have imagined so far. This could mean that all our observations and conclusions of the last 100 years are wrong. The light we see is quanta, and we now know that they behave very capriciously. So how can the speed of light be a stable measure? It's possible that we have created limits for ourselves through this view and constructed a false image that we now need to revise. In reality, light could be much more dynamic and changeable, but what would that mean in relation to our observations of the early universe if the speed of light were indeed variable? We would have to completely rethink our models of cosmic evolution. The observations of the cosmic background radiation that have so far provided us with information about the early universe are based on the assumption of a constant speed of light. Variations could mean that all our calculations of distances and times are wrong. Then our estimates of the age of the universe and the speed of its expansion would also be wrong. This could explain why the Webb telescope shows us galaxies that are so old that they shouldn't even exist. We normally measure the age of galaxies using the red shift of light. When the universe expands, the light is stretched and changes to a reddish color. However, if the speed of light is not constant, our measurements of the red shift are also incorrect ultimately. However, this does not mean that Einstein, Hubble, and all the others who built up our cosmology were frauds. They just delivered the best possible work and explanations for their time and era. They seemed to work very well for almost 100 years, but now it turns out that these theories are incomplete, and we need to open up our science to new dimensions of truth. We could possibly explore a holographic universe only through our minds, but we still have to learn the techniques to do so. Think about it. In the 1970s, there was a man with supernatural sensory perception who could only examine Jupiter through his inner spiritual vision. Ingo Swan's work is often hushed up today, but Swan described the planet's atmosphere almost perfectly and even saw its fine rings, which were only discovered by the Voyager 1 probe in 1979. Before we become such superb brains, the age of quantum computers will probably dawn. These extremely powerful computing machines should, among other things, help us to better understand the true nature of the universe and show us where our previous mistakes lay. Is the world we see an illusion? Physicists have shown the universe may not exist as we perceive it, and what we consider real might be a perfect illusion. We live and explore within this illusion, questioning if matter is real while our interactions with objects like plates and food suggest matter exists. Recent studies suggest it might be a hollow projection for our experience. This theory proposes that our bodies are just condensations in three-dimensional space, possibly controlled by what some call a soul. Einstein's theory of relativity, once fundamental, is now challenged by modern theories like quantum gravity and string theory. These new ideas reveal that space and time might be more flexible than assumed, and gravity might be a curvature of spacetime rather than a force. Quantum mechanics suggests that information about our three-dimensional universe could be stored on a two-dimensional surface, leading to the concept of a holographic universe. Here, gravity is a property of this projection, and consciousness plays a crucial role in shaping reality. Scientists are also questioning the constant speed of light, which could impact our understanding of the universe's age and expansion. Advances in quantum computing and new scientific methods may be needed to explore these concepts further. As we develop these tools, we might uncover more about the true nature of the universe and our place within it. The exploration of whether the world we perceive is an elaborate illusion continues to captivate physicists and philosophers alike. Beyond the realms of classical physics and into the depths of quantum mechanics, the very fabric of reality appears increasingly mutable and enigmatic. At the forefront of this inquiry is the notion that our conventional understanding of matter, space, and time may be inadequate to explain the intricacies of the universe. Recent advancements in theoretical physics, particularly through frameworks like quantum gravity and string theory, challenge Einstein's once unified view of space and time. These theories suggest that at the smallest scales of existence, where particles behave unpredictably and phenomena defy classical logic, our concept of a solid, deterministic universe begins to unravel. Quantum mechanics reveals a realm where particles can exist in multiple states simultaneously, and where observation itself alters the outcome of experiments. An unsettling departure from the certainties of Newtonian physics. Central to these discussions is the concept of a holographic universe, where three-dimensional reality is perceived as a projection from a two-dimensional surface. This hypothesis, rooted in quantum mechanics and cosmology, proposes that all the information that constructs our spatial dimensions and physical phenomena could be encoded on a boundary at the edge of the universe. This boundary acts like a cosmic screen, displaying a rich tapestry of stars, galaxies, and matter, yet fundamentally existing as a complex interplay of information rather than tangible substance. Moreover, the role of consciousness in shaping this perceived reality adds another layer of intrigue. While consciousness remains elusive in scientific terms, its potential influence on quantum phenomena has sparked hypotheses suggesting that our perceptions and interpretations of reality may actively participate in its manifestation. If consciousness indeed plays a role akin to an observer collapsing the wave function in quantum mechanics, it implies that our understanding of reality might be intimately linked to our subjective experience and awareness. The exploration of fundamental constants, such as the speed of light, further challenges our established models. Einstein's theory of relativity, which posited the speed of light as an unyielding constant in the fabric of spacetime, could face revision if new discoveries reveal variability in this parameter. Such revelations would not only necessitate reevaluating our cosmological models but also redefine our understanding of how light and information travel across the vast expanses of the universe. Advances in technology, particularly the development of quantum computers, hold promise in unraveling these mysteries. Quantum computers, with their ability to compute complex algorithms and simulate quantum states, offer a glimpse into potential realities and scenarios previously inaccessible to classical computers. They may provide insights into the underlying structure of the universe, the nature of consciousness, and the fundamental laws that govern existence. As humanity stands at the threshold of this scientific frontier, the quest for a unified theory of everything continues unabated. The search for a theory that harmonizes quantum mechanics with general relativity remains one of the greatest challenges of modern physics. It beckons scientists to venture beyond traditional boundaries, embrace unconventional hypotheses, and pioneer new methodologies that may ultimately unveil the true nature of the cosmos. In conclusion, the idea that the universe could be a holographic projection challenges our perception of reality and invites us to reconsider the very foundations upon which our scientific understanding rests. It urges us to explore the potential interplay between consciousness, quantum mechanics, and cosmology, offering a pathway to a deeper comprehension of existence itself. In the quest to understand the nature of our universe, physicists and cosmologists have been grappling with profound questions that challenge conventional wisdom and push the boundaries of human knowledge. At the heart of these inquiries lies the intriguing possibility that what we perceive as reality may be fundamentally different from what it appears to be. One of the most intriguing concepts emerging from modern physics is the idea of a holographic universe. This hypothesis suggests that the three-dimensional reality we experience could be a projection from a two-dimensional surface, much like how a hologram works. This concept originated from attempts to reconcile quantum mechanics with Einstein's theory of general relativity. In quantum mechanics, particularly in the study of black holes and their thermodynamics, scientists observed that the information content of a black hole's event horizon seemed to be proportional to its surface area rather than its volume. This observation led to the proposal that the entire universe could be perceived as a hologram, where all the information that makes up our reality is encoded on a distant boundary. The holographic principle suggests that the universe as we know it, with its galaxies, stars, planets, and all observable phenomena, may be analogous to a three-dimensional projection of information stored on a cosmological horizon. This concept challenges our intuitive understanding of space and time, suggesting that they may emerge from a deeper, more fundamental structure at the edge of the observable universe. Moreover, the holographic principle implies a profound interconnectedness between different parts of the universe. Every point in space could be intricately linked to every other point through this underlying informational network. This interconnectedness could potentially explain various cosmic mysteries, such as the uniformity of the cosmic microwave background radiation and the distribution of galaxies on large scales. Recent advancements in theoretical physics, particularly in the study of quantum gravity and string theory, have provided additional support for the holographic principle. String theory, for instance, posits that fundamental particles are not point-like objects but rather tiny vibrating strings. These strings exist in a higher dimensional space that could potentially accommodate the holographic nature of our universe. Furthermore, the notion of a holographic universe raises intriguing questions about the nature of consciousness and perception. If reality is indeed a holographic projection, then our perception of the world could be likened to watching a movie. The scenes appear vivid and real, yet they are fundamentally constructed from light and information. Consciousness, then, could be seen as the process through which we interpret and interact with this projected reality. The implications of the holographic principle extend beyond theoretical physics into philosophy and metaphysics. It challenges traditional dualistic notions of mind and matter, suggesting a more integrated view where consciousness and the physical universe are intertwined. This perspective aligns with ancient philosophical traditions that view the universe as a unified whole, where every part reflects the entirety. Moreover, the holographic universe concept prompts us to reconsider the role of perception and observation in shaping reality. Quantum mechanics has already shown us that the act of measurement can influence the behavior of particles, a phenomenon known as the observer effect. In a holographic framework, this effect could imply that our observations not only reveal aspects of reality but actively participate in its creation. From a practical standpoint, exploring the implications of a holographic universe could revolutionize our approach to understanding and manipulating space, time, and matter. It could inspire new technologies based on harnessing information and quantum principles, potentially leading to advancements in computing, communication, and even our understanding of consciousness itself. However, the holographic principle is not without its challenges and controversies. Critics argue that the concept remains speculative and lacks direct empirical evidence. While indirect support comes from studies of black holes and quantum entanglement, direct observational confirmation of a holographic universe remains elusive. Nevertheless, ongoing experiments and observations, such as those conducted with advanced telescopes and particle accelerators, continue to probe the fundamental nature of reality. These endeavors seek to uncover evidence that could either validate or refine our current understanding of the universe's holographic nature. In conclusion, the concept of a holographic universe challenges us to rethink fundamental aspects of reality, from the nature of space and time to the role of consciousness in shaping our perceptions. It invites us to explore new avenues of scientific inquiry and philosophical contemplation, promising insights into the deep mysteries that surround us. As our understanding evolves, so too may our perception of ourselves and our place in the vast tapestry of the cosmos.